Hello everyone. In this tutorial we will learn how to solve one-dimensional heat equation in Matlab using pdepe function. So let's start. So we have this question. You have the heat equation in one dimensional that is given as this: del u by del t is equal to 3 into del square u by del x square, and we have the initial conditions as this and the boundary conditions is given by this. Now we want to solve this partial differential equation in Matlab using pdepe inbuilt function. So let us see how we can do this. So as I have told, we will be using pdepe functions. So before you write the code, you need to rewrite your equation in the form that pdepe solver expects. So what is the standard form of pdepe? This is the standard form. You need to first rewrite your equation in this form. So if you see, our equation of heat is given as this, and you can see that the coefficient of del u by del t is given by this c. So in our equation we can find that our c is equal to 1, and what will be the value of m? This will be equal to 0. And if you can see and compare the given equation with our equation, you can see that what will be the value of f? F will be equal to 3 into del u by del x. And what will be the value of s? The value of s will be equal to 0. So first step is that we need to rewrite our partial differential equation in the format that pdepe solver expects. Now next we will write the code for the boundary conditions. So what is the standard format for the boundary condition that is expected by the solver? This is the standard format. So you have to define your p and q for the left and right boundary. So if we talk about the signature function, it looks like the boundary functions have this type of signature function. So here xl and ul corresponds to u and x of the left boundary, and xr and ur corresponds to u and x of the right boundary. And t is what? T is independent time variable. What is this PL and QL? This corresponds to the for the left boundary, and PR and QR corresponds to the right boundary. So what we have to do, we have to see our boundary conditions, and then we have to rewrite our boundary condition in this format. So if we see our example, in this case what we are discussing where my left hand boundary is given to be 0, and at 1 distance I have temperature of 1. So what I have done, I have written the boundary condition that the solver expects. So this one will be the value of PL, and this one is the value of QL, and this one will be the value of PR, and this one will be the value of QR. PL means I am talking about the left boundary, and what is this? PR, I am talking about the right boundaries. So you have first rewritten your boundary conditions. If you can see, this is nothing but this boundary conditions only I have written in the format so that it matches with the one that is expected by pdepe inbuilt solver. And the next one is that we need to write down the initial conditions also, and for this we will use this type of signature function. This is expected by pdepe solver. So let us see the Matlab code. Once you have rewritten everything in the form which is expected by pdepe solver, you can code further. So you can see that what I have done, I have created a function that's name is heat underscore equation, and this m is 0. How this m is 0? I have already told you. In this you can see that we have our m equal to 0, so we need to specify with the same nomenclature. This is understood by pdepe solver. So here we can see that the value of m is 0. Then I have divided x from 0 to 10 with 50 points. Like you have the length x, that is I am talking about the space between 0 to 10, and it is divided by 50 points which is equally spaced. Then the t is taken from 0.1 to 10, and again there are 50 points in between them where the iteration will take place. Now we need to call the inbuilt MATLAB solver for partial differential equations in one dimension, that is pdepe. Now here the input arguments will be m, that you have seen that this partial differential equation here m is 0. It is written on the top also. And then this is I am calling the other functions where I have defined my boundary conditions, initial conditions and the equation. So these are for the equation. This I am calling where my equation is defined. This I am calling where my initial conditions are defined, and this I am calling where my boundary conditions are defined. This is x is a space and t is time. So then since this is only one system of equation, so we will give a variable u1 to the first partial differential equation. You can use this pdepe to solve system of coupled partial differential equations also. So accordingly you will increase the variable, and then you can store the components over here. Like if you want the second component, you can write 2, or the third component you can write 3. Then this is for plotting the graph. This is for labeling. This will give us a surface plot between x and t and u1, that is the heat. Now this is the main function. So this I have written as where we will define our equation. So as I have told you before that in this equation our c is equal to 1, f is equal to this, and s is equal to 0. How does it came? See the equation which we are talking about, if we match it with the form which pdepe solver expects, we can see that here our c is equal to 1, f is this, and s is equal to 0. So the same thing we have written over here. M is already defined over here, and the other three things we will define it over here. And then we will again call another function which takes the initial condition. Here you can write, or if you have other heat equations, your initial conditions over here, it can take other functions of x also. So this is a particular case which we are talking about. You, according to your equation, you can modify the initial conditions over here. Now this function that is named as pdx4bc, this is only the name of the function. This one collects the boundary condition. So here, as I have told you, again what you have to do, you have to rewrite your boundary condition in the form which is expected by pdepe solver. So you can see that for this equation which we are talking about, we have this boundary condition, and then you can see that our PL is equal to this UL, that is a left boundary, plus QL is what? 0. So we will define it as PL is equal to UL and QL is equal to 0. So the work of our left boundary condition is finished. Now we will see the right boundary condition. So you can see that here I have a right boundary condition. Here my PR will be this, that is UR minus 1, and QR is equal to 0. So this is PR equal to UR minus 1 and QR is equal to 0. So this was the complete programming by which you can numerically solve the heat equation using inbuilt pdepe solver. So what you have seen that the main step is to rewrite the equation in the form that is expected by this pdepe solver. Now what we will do, we will copy paste this code in the MATLAB and we will simulate, and then we will see what is our output. So let's copy paste the code. So now I have copy pasted the code over here, and you can see that it is the same code as I have shown you in my PowerPoint presentation. Now to run this code, what I will do, I will press this run button, and you can see that I got this figure. So this is a surface plot. Now if you want to see that how the heat is changing in bit of space and time, what you can do, you can just make a projection or see the projection of this. And here you can see that this one is what, this one is a space is from 0 to 10, and time is also from 0 to 10, and you know that we discretized it between the 50 points. So here are the 50 points. And now what I want to see, I want to see how much heat is there in this space. So you can see that at time 0, the entire, you can say, wire was having the heat, because the yellow is showing the temperature. So this you can see that yellow is the highest temperature and this blue one is the lowest temperature. So you can say that by looking at this figure, that at time 0 the whole fire was heated, and then as the time is increasing, say that the heat is decreasing towards the left bottom. This blue portion is saying that the left side is becoming cooler and the heat is concentrated towards the right hand side. You can see that how you can easily solve or find out the numerical solution of partial differential equations with the help of pdepe solver, which is an inbuilt function in Matlab. So I will end this tutorial over here. Thank you.